to this lesson on function notation with me, Elena. In this lesson, we are going to dive into the world of functions so that you'll be prepared to deal with these sorts of questions whenever they pop up on the SAT. Let's go ahead and get started by asking, what is a function? Well, the best way to think of it is that a function is like a vending machine for numbers. Now imagine that you're at a vending machine and you want to get a Sprite. So you push a button. Let's say you push the button labeled A6. You push A6 and out comes a Sprite every single time. That's exactly like what a function does, just with numbers instead of Sprite. So imagine that we've got a machine. The machine is the function. We have an input that we put in, for example, the number 5. And that input leads us to the same output every time, for example, the number 8. We've pushed that button A6 to get our Sprite. We've put in an input to get a specific output through this function machine. Okay, so there's a couple of specific rules that we should understand about inputs and outputs. Each input has exactly one predictable output. Every time I press A6 on my vending machine, I am going to get a Sprite, and the same is true of these inputs and outputs. When I plug 1 into a function, we should always get 5 back. Each input gives us one specific output. So if we plug 1 into that same exact function and get 10, then there's something clearly wrong. Like if I go to the vending machine and I push A6 and instead of getting a Sprite, I get a water bottle, then something's wrong with that vending machine. Just in that same way, these function machines should always give us one predictable output for one specific input. However, it's possible that many inputs could end up giving us the same output. So for one function, perhaps the only way to get 5 would be to plug in 1, but for another function, we could get 5 by plugging in either 1, 2, or 3. You can think of it as if there's different vending machines, right? Not every single vending machine I come across in my lifetime will give me Sprite if I press the button A6. Maybe some vending machine will give me something completely different if I press A6. The point, however, is that when you're at a specific vending machine, it should follow rules. And when you're dealing with a function, it too needs to follow specific rules. That each input gives us one output, and that many inputs could end up giving us the same output depending on the rules of the function machine. So let's go ahead and practice these rules that we've learned. Which of the following is false about functions? Is it A, there may be many numbers you can plug in to get the same number back? Well, yeah, A is one of our function rules that we just reviewed in that last section. So A could be true. What about B? Functions can take a number in and give a number back. Yeah, that's the definition of a function. We put a number in, we get a number out. So A and B are both true. What about C? Plugging in a number may give a different result each time. Nope, C is false. It breaks our function rules. We need to know with functions, just like with vending machines, that when we put in a number, we are going to get the same result every single time, so that the rules of the machine are being followed and it functions correctly. Pun intended. Okay, now that we understand these function rules, let's talk about function notation. What is it? Well, function notation gives the function a name and a variable. What does that look like? Well, let's go ahead and see if we can put this into practice. Let's say that we have a function. The function of x is equal to 3x plus 8. Okay, so that's our machine. When we put in a certain number, we're going to get a certain result. The rule for this function, if we were doing this according to function notation, would be to multiply the input by 3 and then add 8. So whenever we input a number into this function, which is signified by that x, we're going to multiply that x input by 3 and then add 8 to it. An example would be input of 4. So f of 4 would be equal to 3 times 4 plus 8, which would ultimately be equal to 20. All we did there was plug in that input into the function itself and then solve it. And then we know what f of 4 is equal to. The note would be that if input is equal to 4, then output is equal to 20, which is basically just another way to rewrite and explain what we just did. So function notation gives that function a name and a variable so that we can understand how to use the function. This is just breaking down the way that we might solve a function. So let's try another example. How about this function? G of x is equal to x divided by 2 minus 5. So the rule here for the function is that we're going to divide the input x by 2 and then subtract 5. As an example, let's use the input negative 6. That would be negative 6 divided by 2 minus 5, which would ultimately lead us to negative 8. Our note here would be that if the input is equal to negative 6, then the output becomes equal to negative 8. That's just like our vending machine rules, right? If I press A6, I get a Sprite. If I input negative 6 into this specific function, then I will get negative 8. Let's look at another. H of A is equal to A squared plus A. So the rule here is that we square the input and then add the input to what we just squared. Let's look at an example where the input is 3. So 3 squared plus 3 would equal 12. And our note here would be that if the input is 3, then the output is 12. See how in all of these examples, we're able to break down that rule by simply looking at the function, we can work through an example, and then ultimately we get that note, which is basically the rules of the vending machine explained to us for a particular input. Okay, nice work. Let's go ahead and practice. For the function g of x is equal to 3x minus 4, what is the value of g of 0 plus g of negative 2? Okay, well here, what we need to do is find g of o, find g of negative 2, and then just add those two together. We've got in our notation here this function, and we've got that rule that we need to multiply whatever input we put into this function by 3 and then subtract 4. So let's go ahead and do that, starting with g of 0. So g of 0 is equal to 3 times 0 minus 4. Of course, 3 times 0 is just 0. So g of 0 is equal to 0 minus 4, which is simply negative 4. Okay, so we have a value now for g of 0. Now we need to find the value of g of negative 2. So let's do the same thing all over again. We'll plug in negative 2, so we get 3 times negative 2 minus 4. That gives us negative 6 minus 4, which ultimately gives us negative 10. So we found g of 0, negative 4. We found g of negative 2, which is negative 10. Now we're being asked about the value of those two things added together. So we want to plug in what we just found thanks to these functions that we worked through, which means that g of 0 plus g of negative 2 is negative 4 plus negative 10, which of course is just without the parentheses there, negative 4 minus 10, which ultimately leads us to negative 14, which means that for this function, g of x equals 3x minus 4, the value of g of 0 plus g of negative 2 is negative 14. And we were able to work through this problem because we understand how functions are taken down. We know the way that they work, we know how to read their rules, and ultimately use our inputs to get to the right answer. Okay, now that we've got this under our belt, it's time to start looking at function problems on the SAT and some of the more specific ways in which the SAT will try to trick and trap you with function problems. Let's go ahead and start by taking a look at functions defined by specific numbers. What are these? Well, some function questions won't give us formulas. Remember how we had those formulas that gave us a specific rule for what we ought to do with our inputs? Well, sometimes we don't get that on function questions on the SAT, which can initially seem really intimidating. How are we supposed to solve any sort of function question if we don't have a formula? Well, let's go ahead and take a look at such a problem. The function f is defined such that f of 0 is equal to 3 and f of 2 is equal to 5. what is the value of f of 0 plus f of 2? Notice how we don't get a formula here like we did in all of our previous example problems, but remember, the SAT will always give us just enough information to solve the problem. It usually won't give us any more information than we actually need, but it will always give us just exactly what we need to get to the right answer. So let's think critically about this problem. What we're trying to find here is f of 0 plus f of 2. Now, we don't have any formulas to figure out this function f, but what we do know is that f of 0 is equal to 3 and f of 2 is equal to 5. It's almost too simple, but it's tricky because we're so used to seeing functions written with their formulas. Know that some function questions won't do that, but they will give you information that we can plug in. So all we have to do, since we actually know the values of f of 0 and f of 2, is substitute. So 3 plus 5, f of 0 plus f of 2 is equal to 8. That's exactly the same thing as f of 0 plus f of 2 being equal to 8, because we know that f of 0 is equal to 3, and we know that f of 2 is equal to 5. Let's go ahead and practice with a similar problem. The function g satisfies g of negative 1 is equal to 2, g of 0 is equal to 3, g of 1 is equal to 4, and g of 2 is equal to negative 5. What is the value of g of negative 1 times g of negative 2? Now, in this particular problem, we aren't given any formulas, but we are given a lot of values. So remember, we have everything that we already need to solve this problem. We know that we're trying to find g of negative 1 times g of 2. But then again, we already know those values because we're told what the function g satisfied. We know that g of negative 1 is equal to 2, and we know that g of 2 is equal to negative 5. So all we need to do is substitute those two numbers in for those functions, and then we get negative 10. So ultimately, we didn't need the formula here because we were given what the function g satisfies in a couple of specific instances. The SAT wants you to be able to recognize when you need to substitute so that you can do so confidently, just like we've done in these problems. All right, nice work. Let's go ahead and turn our attention now to functions defined by tables. These questions are all about interpreting the tables that contain the data. Let's go ahead and take a look at an example. So in this table, we have x, and then we have h of x. We've got some numbers underneath each. Well, how do we interpret this? For every value x on the left, so 0, 2, 3, and 5, when you plug it into h, you get the value on the right, 1, negative 3, 4, and 5. So basically, we're plugging in the numbers in the x column in order to get the numbers in the h of x column. Now, if that seems a little bit confusing, don't worry. We're going to do a lot of practice problems to make sure that you completely understand how this system works. Let's go ahead and start with the first one. So h of 0 would be equal to 1, right? We just took a 0, plugged it in for x, and we got the answer 1. What about the second column? H of 2 is equal to negative 3. So we're just plugging in that x, getting that h of x value. Same for the next column. H of 3 is equal to 4, and h of 5 is equal to 5. So all that you have to do here is understand what needs to be plugged in where. That's so much of function problems. Just making sure that you understand where the numbers need to go. So we plug in our x's to get this h of x value. Okay. So, for which value of x is x equal to h of x? Well, if we look at all of this data that we just gathered, it's that very last value of x, 5, because there, x, 5, is equal to h of x, 5. So that's the way that these functions defined by tables problems tend to look. You might be asked about what value is the function defined a specific way. You're just being asked to plug in some data, interpreting the table correctly. Let's go ahead and practice what we've learned. For which value of x is x equal to negative f of x? Okay, so let's go ahead and take a look at the table that we're dealing with. Now we've got our x values and we've got our f of x values. Let's go ahead and translate this data so that we can figure out which value of x makes this equation true. So the first would be that f of negative 2 is equal to 8. Remember, we're just plugging in that x value and making it equal whatever the f of x is equal to in that column. Okay, next, f of 0 is equal to 5, f of 2 is equal to negative 2, and f of 7 is equal to negative 10. Now, out of all of these values that we translated over from this table, the only one that makes x equal negative f of x is when x is equal to 2, right? And then we have f of 2 is equal to negative 2, which, if we then reversed, would be x is equal to negative fx, or 2 is equal to negative f of 2. Great. So now that we understand how to translate the data in these tables and use it to help us evaluate some function problems, let's go ahead and turn our attention to dealing with multiple functions. Well, this sounds a little bit intimidating at first, but luckily for us, this is basically the same as dealing with one function. So let's go ahead and take a look at our table here. Now, we already know how to deal with tables, so what would we do with a table like this? Well, let's say we were dealing with this question. This is a first multiple function question we can look at. For which value of x is f of x plus g of x equal to negative 5? Okay, so let's go ahead and just do the exact same thing we just did with all of our tables. We know that f of 1 is equal to negative 1, and g of 1 is equal to 4, if we're plugging in that data correctly. Let's plug in the input of 2. Then we know that f of 2 is equal to 2, and g of 2 is equal to 5. Let's plug in our input of 3. f of 3 is equal to negative 4, and g of 3 is equal to negative 1. Finally, input 4. f of 4 is equal to negative 1, and g of 4 is equal to negative 6. So we just used those exact same skills that we used on tables and applied them right to this problem that deals with multiple functions. Well, what do we do now? We've got all of our information from the tables, and we need to figure out for which value of x is f of x plus g of x equal to negative 5. Well, what we need to do is add these together and see which one brings us to negative 5. So, if we added f of 1 and g of 1 together, negative 1 plus 4, we would get negative 3. So, not f of 1 and g of 1. What about value of 2? So f of 2 equals 2, g of 2 equals 5, 2 plus 5 is equal to 7. Nope, that's not the right value of x. What about 3 as the value of x? Negative 4 plus negative 1. That equals negative 5, which means that's going to be the correct answer. But let's just check the last option to be sure. Let's use that value of 4, which would lead us to f of 4 equaling negative 1, g of 4 equaling negative 6, and ultimately, if we added those two together, would give us negative 7, which is not correct. The only value of x that allows f of x plus g of x to equal negative 5 is when x is equal to 3. So all that we did here is really the exact same thing that we did when we looked at functions defined by their tables. We just used that and applied it to two functions instead of one. And then we just substituted those values. That's all that we have to do on these sorts of function problems. Let's go ahead and try a practice problem together. For which value of x is x plus q of x equal to p of x? Okay, so we've got our table. Let's do first things first and translate this data. So if x is equal to 0, then p of 0 is equal to 3, q of 0 is equal to 5. If x equals 2, then p of 2 is equal to 9, and q of 2 is equal to 7. If x equals 4, then p of 4 is equal to 8, and q of 4 is equal to 3. Finally, if x is 6, then p of 6 is equal to 10, and q of 6 is equal to 7. Now that we've gone ahead and figured out the data in this table, what we need to do with all of this information we've gathered is plug it into this equation that we've been given to see for which value of x does the equation become true. Let's go ahead and start off with the value of x of 0. So here we would get 0 plus q of x, which is 5, is equal to 3 p of x. That's not correct. 0 plus 5 is equal to 5, not 3. This equation does not work. So we know that the value of x can't be 0. What if the value of x was 2? Then we'd get 2 plus q of x is equal to p of x. 2 plus 7 is equal to 9. Well, that's correct. That actually works because 2 plus 7 is 9. Let's hold on to this choice and just check the other answers to be sure. What if x was equal to 4? Then we would get 4 plus 3 is equal to 8? No, that's not correct. 4 plus 3 is equal to 7. So the value of 4 does not work for this equation. And finally, what about the value of x as 6? Then we would get 6 plus 7 is equal to 10, which again does not work. 6 plus 7 is 13, not 10. So when we're dealing with this multiple function equation, all we had to do was plug in the data correctly, look at the equation that we were dealing with, and then make sure that we were substituting in the right information, so that ultimately the value of 2 is what makes this equation true. Okay, now that we've got a handle on how to deal with multiple functions, it's time to deal with multiple functions in a new form, nested functions. Nested functions refers to a function inside of a function. That would look like this. Basically, we do the same thing with nested functions as we do with regular functions, as we do with multiple functions either. We're just dealing with many functions instead of one. Let's take a look. So, we've given two definitions here for the functions f and g. The function of x is equal to x squared, and g of x is equal to 4 minus x. So we've got those two defined, and now we're asked, what is the value of f of g of 1? So do you see how g of 1 is inside parentheses, and then outside of that is f? So g of 1 is nested inside f of g of 1. So we're dealing with this function inside of a function, and what we want to do is work from the inside out. We want to start by figuring out what is g of 1, what number would that be, and then plug that into the function for f. This might seem a little confusing, so that's why we're going to go ahead and work through a problem together. The first step that we want to take is to find the value of g of 1, that inside function. So we already know the equation for g of 1, which is g of x is equal to 4 minus x. So all we need to do is plug in that input 1 to see what we get. So g of 1 would be equal to 4 minus 1, which means that g of 1 is equal to 3. Perfect. Next, step 2 is to plug that value into f, the larger function on the outside. That would mean that instead of having f of g of 1, we just have f of 3, because we know that f and g of 1, if they were paired together like that, we know that g of 1 is equal to 3, so we can just put 3 in the place of g of 1. Okay, so we know the equation then for f of x, which is equal to x squared. So f of 3 is equal to 3 squared, which means that f of 3 is equal to 9. Okay, so that means that ultimately we've got the answer, that f of g of 1 is equal to 9. Because we started from the inside out, we used our function rules, we kept our work clear and straight as we went along, and ultimately we were able to find the right answer. Let's go ahead and sum up what we've learned. We've learned that functions are machines, just like vending machines, that take inputs in and return predictable, consistent outputs. Function notation uses a name and a variable to give you a rule for plugging in. Functions can be added, subtracted, multiplied, and divided using their expressions just like any other expression. Functions can be nested, in which case we complete their rules from the inside out. As long as you're familiar with the rules for how functions are used, and as long as you're familiar with how functions might appear and be tested on the SAT, then you'll be well on your way to being prepared to deal with these problems whenever they might pop up.